Hello, scientists. Welcome to Lab 7.05, Waves number 1. We are going to look at the electromagnetic spectrum and all the different sorts of waves that are part of the electromagnetic spectrum. Let's start with this Earth guide. We can play around with this simulation a bit. This is a useful simulation to look at least briefly, because it walks you through all the different sorts of waves, and you can see the wavelength and frequency for each type. We'll start down here with radio waves that are fairly low energy. You can see here on the energy diagram, they're low energy with a long wavelength and a low frequency. As we move up in the electromagnetic spectrum to other types of waves, like AM and FM radio waves, and the kinds of radio waves that are used in RFID tags for inventory control. You might have seen those in a store stuck to a box, or the kind of waves we use for Doppler radar. There, you can see that the wavelength is getting a little bit shorter, and as a result the frequency is getting up a little bit higher. Frequency means more waves are going by every second. So here we are, microwaves. You can see that the frequency is getting higher, more waves are going by every second, and the wavelength is getting shorter. These waves carry more energy. As we go up to infrared radiation, we get even shorter and more frequent, and the energy goes up. As we go to visible light, you can see that the energy goes up, the wavelength gets shorter, and the frequency gets higher. And so it continues up to ultraviolet light, which we can't see. X-rays, which you know can be quite powerful. You want to avoid getting too many of those if you can. And you can see X-rays, the energy has gone up quite a bit, and so has the frequency, and the wavelength has gone down. And as we get to gamma rays, which are the result of nuclear decay, you might encounter these if you're very near a nuclear reactor, nowhere near a nuclear plant. They're very well shielded. Gamma radiation is the most dangerous. It is used in nuclear medicine. If you know someone who's had cancer and gone in for radiation treatments, this is what they use to treat cancer, by irradiating those cancer cells with lots of high energy. You see, high energy, short wavelength, high frequency. So that's a basic introduction to the electromagnetic spectrum, and you can play around with this simulation some more if you'd like. Our second simulation here has a short quiz at the end that's very similar to some of these questions. So click into this and hit play, and it'll walk you through some important information, and it has a quiz at the end. I'll show you briefly.
When you're ready to discover more, press the start button.
So click into this, turn your sound on and click start, and it'll give you a little presentation about the electromagnetic spectrum. So once you've answered these questions, go to this particular simulation, and we're going to look at the difference between transverse and longitudinal waves. So let's hit play and see what happens. You can see that a transverse wave, each individual particle doesn't move on the x-axis here. It just goes up and down on the y-axis. So it just goes up and down. So this is a transverse wave. If you think of a stadium wave, where you might be in a football stadium or a soccer stadium, and you've seen people go woo, and then they put their arms down, and that kind of travels around the whole stadium. That's a good example of a transverse wave. Let's pause this one and look at a longitudinal wave. Sound is more of a longitudinal wave. The air particles bump up against each other and then come back, and it travels primarily along the x-axis. Particles move up and down here, and the wave moves along the x-axis. Here, particles move along the x-axis and the wave moves in the same direction. So those are some important differences between a transverse wave. Particles go up and down in a transverse wave, but the energy travels along the x-axis, and both the particles and the energy travel along the x-axis in a longitudinal wave. Now that you know the difference between the transverse and longitudinal waves, you can answer question 5, and we can go on to part 2, exploring wave characteristics. We're going to mess around with the simulation, mess around with these sliders, and see what happens when we change the amplitude of a wave and change the frequency as well. So here we are in the PhET simulation. It starts out looking like this, where it's manual and it has a fixed end. If you want it to look like the simulation I'm currently with, put it on oscillate and put it on no end. And you can hit pause if it bothers you, the motion. Right now, we're going to start answering those first couple questions in part 2. We're going to play with the amplitude slider and see how that affects the wave. So I'll move the amplitude slider around. You're welcome to do it on your own as well. Please do. So let's make the amplitude smaller at first. And what does that do to the height of the wave? Let's make it larger. Notice what's happening to this piston here. We'll step it a little bit. When the amplitude is large, this piston here is traveling a great deal of distance from the midline here. Then if we turn the amplitude down and step it, it's only going very slightly above and below. Let's turn the amplitude back up, way up, and let it play. So you can draw your own conclusions about how amplitude affects a wave. Now let's try frequency. I'm going to turn the amplitude kind of down to the middle here. We'll let it play here. I'm going to turn the damping down, which just means the waves will continue. Let's turn up the frequency. What happens to the total number of waves you see here? Right now we're seeing about 1, 2, 3, 4. Here, I'll stop it. 1, 2, 3, 4, 5. When we've got a high frequency, we see 5 wave patterns. Let's see what happens when we turn that down. We turn it way down and we pause it. We don't even have 1 full wavelength here. We only have about half. So hopefully you have some good ideas about how amplitude and frequency affect waves. Now you should have the information to answer questions 6, 7, 8, and 9. If you need help with question 8, you can go back up and look at these waves as a reference. Let's continue here. Question number 10, you need to write a definition of the word frequency as it relates to waves in your own words. You can also explain how the damping slider works to change the wave. Remember, the damping slider is right here, and if you want to see how damping affects the wave, I suggest maybe putting amplitude and frequency kind of in the middle and damping it using a lot of damping or little damping and drawing some conclusions. Now that you've explored damping, you can click all of these buttons here at the bottom of the simulation. Our goal here is to discover the differences between the manual, oscillate and pulse buttons and how those affect the way the wave behaves, we also need to discover the differences between the fixed end, loose end, and no end buttons here on the right in the sim and see how those affect how the wave behaves. Now you have the information you need to answer questions 13 and 14 since you've been able to play with some of these buttons in the simulator. Let's go down to question 15 where we're asked to compare and contrast. That means to find similarities and differences in the three waves shown above in figures 1, 2, and 3. Use the words frequency and amplitude. Frequency is how the number of waves that come by every second or every amount of time. You can see that the frequency, the number of waves that come across in a particular chunk of time, is different here. And amplitude, how high a wave is, how far away is it from the midline here, is different in some of these waves. So compare and contrast, find similarities and differences between the three waves in figures 1, 2, and 3. Remember to use the words frequency and amplitude in your answer. So for this next part of the lab, you're going to need a piece of paper. It doesn't have to have tape on it. And some kind of markers. Maybe a highlighter, dry board marker, good old coloring markers, Sharpies, something that doesn't have a sharp point because we're going to be drawing on the screen of your laptop. So a good old regular ballpoint pen, probably not the best thing to press into your laptop. If you have a pencil that's very soft and kind of dull, that might work. Ideally, you'll have two colors. Some chalk might work. That's soft enough that it probably won't press on your monitor too much. Be gentle, whatever you do. So we're going to set up for this by setting the amplitude sliders to high, the frequency, damping, and tension sliders to low. Click the oscillate button. I'll show you how to set this up in just a moment. The no end button, we're going to use pause to freeze the wave. You know what pause buttons look like. We're going to place our blank piece of paper on our monitor and trace the wave and the wave generator. We're going to mark the green dots, and if you're colorblind, every 10th dot is green. I know the blue-green dot color choice was not a great idea for colorblind people. I apologize, but do count every 10th dot if you can't tell which ones are green. And then we're going to label the axes of our graph. So let's go look at the simulation and see what to do. So here's what the sim should look like when you're ready to trace. The amplitude should be pretty high. The frequency and damping should be low. I had better luck with turning the tension to medium here rather than low. You should be on oscillate here, the middle button on the right hand, left hand radio buttons on the bottom, and you should have no end here on the right hand radio buttons on the bottom. I have it paused right now. I'll play so you can see what it looks like. And then I'm going to pause and take my piece of paper, and then I'm going to trace this axis right here. It doesn't have to be perfect. You don't have to trace every one of these little lines here. You can just draw a very light line here for the x-axis. You can draw this here for the y-axis, or you can draw, later you can figure out how far the oscillator goes up and down here for the y-axis. And then trace the wave. And I'm going to put an X on every green dot. So I'm going to trace the wave, putting an X on every green dot, or you can just color it in and make it bigger. So I'm going to take my paper here and just stick it right up against the screen on my laptop and trace this wave. So hopefully you've paused the video and done this yourself. So here's what I got. I labeled, it's a little bit hard to see my axes maybe, But I used a ruler to trace this light green, the middle axis here, the x-axis, and then I used a nice strong Sharpie to trace the wave. I put an X where all the green dots are, and I circled those X's so it's easier to see in the video where my green dots are. I used a little bit of tape to attach the piece of paper to the screen, and it helped hold it steady while I drew. Now the next thing we're going to do, I'm going to use a different color. I'll use red so it's easier to see. I'm going to let the wave play a little bit, and I'm going to try to pause it when it's in a different spot. And then I'll trace it again, and the idea here is to look at where the green dots are in relation to each other. Another trick you might want to use when you're tracing your wave is to turn off the lights in the room so that your monitor glows a bit more and it's easier to see the wave. So I put my paper up to the screen again and traced the second wave in red here, and I also made a red X where the green dot was and circled that in green again. And you can see that the green dots here have the same relationship to each other in every case. They stay on the same y-axis. The green dots don't move along the x-axis, they only move along the y-axis. So you can imagine, based on what we learned about transverse and longitudinal waves, what kind of wave this is. Hopefully you got similar results. If you're still going to try this yourself, please make sure that you turn off the room lights. It really helps. And you can kind of lift your paper a bit if you need to find those green dots. Tape helped a lot. So good luck with trying this on your own. It's pretty cool. You should, you can even do a third wave if you have some more colors, and check it out. So when you first draw the wave, observe the amplitude and wavelength. If you pause the wave in another spot, will the amplitude and wavelength change? You can think about that. We already investigated that a bit. Now, after you pressed play and then pause again so you have a wave in a different spot, we used the same piece of paper, put it on the monitor, and we got a different wave. We're supposed to look at the differences and similarities in our two waves. What happens to the position of the green dots? We talked about that. You may have to do some more tests by pressing play, then pause, and tracing. So maybe doing a third or even a fourth wave is a good idea to really test some of your ideas. 18 here is we're going to investigate how waves behave when the string end is fixed and loose with the manual settings. So we need to change the settings a bit. We need to go to manual setting here, and we'll hit restart. If we have a fixed end, let's see what happens. We'll grab this wrench here. Put one pulse in. And watch it come back. Notice that it went up at first. The wave was on top of this line, and when it comes back, it's reflected. It goes underneath the line. Crazy, huh? So it's kind of an echo. It bounces back. Let's restart this. Look at that one more time. Let's see what happens if we turn the damping. And it's going to come back underneath our line. Let's turn that damping back down. Let's turn the tension to high. Let's restart this. Kind of made a square wave there. So let's now have a loose end and see how that works. Well, when we have a loose end, it doesn't flip. It just comes back right on top, the same way it went down the string. Interesting. So after experimenting with the manual settings with fixed and loose ends, you have the information you need to answer question 18. Now you need to think about sound waves. Remember when we were looking at the simulation earlier here, in part 2, looking at 2 different kinds of waves, we were looking at transverse and longitudinal waves, and we said that longitudinal waves were sound waves. So here's a refresher on transverse and longitudinal waves. A transverse wave, the particles go up and down and the energy goes sideways or longitudinally down the x-axis. Particles travel on the y-axis, the energy travels on the x-axis. A longitudinal wave, both the particles and the energy travel along the x-axis here. The longitudinal wave is much like a sound wave where the air molecules are compressed and then they bounce back when the wave passes through. You might have kind of seen an evidence for this if you've seen a speaker vibrate. If you take the covers off your big sort of floor speakers, you might see them vibrate if you have very loud music on. So now let's go think about this in comparison to the wave we played with in 18. So remember that longitudinal wave and what it looked like. Did it look like this? I'll let you think about it. Remember, longitudinal waves are sound waves. Is this going to look like a sound wave? Are the particles traveling in the same direction as the energy? I've given you a hint here for part 4, the extra credit, making waves. I've copied figure 1 from above in the worksheet, and I've drawn out here one wavelength from crest to crest, and then I've drawn out 2 wavelengths here. And if I want to make a wave that has twice the wavelength but the same amplitude, I'm going to go from crest to trough in what's basically twice the amount of space it takes for the original wave, and then I'm going to go from trough to crest in twice the space. So it's going to take me 2 wavelengths to do this one wave with twice the wavelength. So what I did is I went into the insert menu in Word, went to shapes, I found the squiggle tool, which is kind of a little curly line, and then you can just draw right on top of this here with the squiggle tool. And you can probably do a much better job. In fact, I'll expect you to do a much better job. You can do the same sorts of things, the same sort of thing, copy the figure and draw on top of it with the squiggle tool. Remember to go to the insert menu and grab the little curly thing to draw a wave which has twice the frequency or half the amplitude. It's helpful to mark off the wavelengths with the squiggle tool here so you kind of have a reference. To briefly review what we learned in this lab, we learned about the electromagnetic spectrum and the frequency, wavelength, and energy contained in different kinds of waves in the electromagnetic spectrum and how they compare with each other. We looked at transverse and longitudinal waves in this simulation. We made transverse waves in this simulation, and we looked at the effect of amplitude and frequency. Make sure you understand what amplitude and frequency mean. We also looked at damping. We looked at the differences between having a fixed end and an open end. And we looked at what happens to a particular particle in a wave over time in different phases of the wave where that particular particle is in a transverse wave. And we thought about that, how that compared to a longitudinal wave. So make sure you understand all the major concepts in the lab. Thanks so much for doing this lab with me. This is Miss R signing off on Lab 7.05, Waves number 1. Thanks so much. Bye-bye.